Greetings and welcome to a new video about LC ladder filters. In this example we'll discuss the Bessel response to design a low-pass filter for this specific situation, and the specification we are talking about will be a singly terminated circuit. This is done upon a request from our viewers about this LC ladder filter. It requires actually a zero source impedance. That's actually what we discussed now. Of course, we will see everything step by step in our calculations and verify these in SPI simulations. Okay, we have the following objective. We like to design a Bessel response, passive LC ladder, low pass filter, and the final design should have the source resistance of 0 ohm and the load resistance should be here 50 ohm. That is what is required. And the specifications for this filter will be then a maximum passband ripple of 1 dB, the minimum attenuation we want in the stop band region of 20 dB. The passband frequency is 1 MHz, so at this frequency I need to have at max a gain reduction of 1 dB. That's what the meaning of these two specifications. And the stop band frequency meaning at 5 MHz I need an attenuation at least 20 dB. Alright. So how do we tackle this problem? Okay, let's go look at our solutions. First, the calculations. Step 1 is the passband normalization coefficient we need for our Bessel response. It's called the C sub P. Now, for a given maximum passband ripple, in this case 1 dB, we can determine that normalization coefficient, C of P. Now, that ranges between the 0 and 1, which is a normalization value. If you look at your A max, which then runs in dBs from 0 up to the half power bandwidth value, which is then this 3.01 dB approximately. So that will be translated this into the value between 0 and 1. That's just a translation from A max in dBs into normalization values between 0 and 1. And that will be then determined from a table actually, where you see several values of this passband ripple values. And that also determines the filter order. Now that's the table we will use. Of course, we will not drive this, but that's what you see here. You see here several values for A max. For filter order 1, you have these values, and for 2 up to 10th order, you actually see these values. So what do we need here? Now, in this case, we need a max in dBs of 1 dB, and that requires, actually here you see that 0.59810. That's the, let's say, the value we need as the coefficient for this passband normalization, but we still do not know if it is a second order or third order or fourth order, because that can be different depending on the 20 dB stop attenuation here. So we need to look more carefully. Again, our A max of 1 dB has now translated in the normalization coefficient for the passband of 0.59810. Okay, now we need to first then determine this transition sharpness omega r in order to continue and then design this for a specific filter order. That is really the ratio in this low pass filter configuration, the stop band frequency divided by the passband frequency. Now it's given here in omegas, but just a ratio of course, so you can also go for the F as an FP, and that is in this case 5 MHz divided by 1 MHz, is just 5. Okay. Now, we need to, again, go to the normalizing value, so normalized value. So we actually look at this and make that normalized. So how to do that? That's step 3. So you take this value and then multiply that by the CP we have determined in step 1. And then you get 5 times this 0.59810. That's approximately 3 here, so 2.9905. This is a very important value because we need to use this in our table that will be then brought up shortly. Okay, this is the table I will use. It's the table where you see different filter orders from first order up to 10th order. The vertical axis is given the stop band attenuation you need. In this case, we have 20 dB requirement. And this horizontal axis is what you see as omega r prime, which is our normalized transition sharpness. Okay. In this case, we need 2.9905, that's here. So I will label them, so very close to 3 actually. So I go up by a vertical line, this red line. I also have this pink line, which is our 20 dB requirement. Now I see here some intersection, but you can see already this intersection here, which is very close to the third order. You see already that the first order is definitely not sufficient. Second order is also not that sufficient here, so that can be, of course, not be used. Third order is actually just enough. You might say, well, I might need some safety, so I go for a fourth order. Well, that is possible, of course. You can also go to fifth order, doesn't matter. But a third order is, I think, is now sufficient. Fourth order maybe will be here an overkill. So we'll be going for a third order. Of course, if you go to higher orders, you need more components, etc. So maybe not necessary. All right, so I will go for a third order that will do the job for this design. So let's bring it here, and then we see here as set from the table for this requirement of omega r prime of 2.9905 from this graph, n is 3. So we need a third order Bessel response filter. This is also a very important step, which is the frequency scaling factor k sub f, and that is actually equal to the omega p, which is our passband frequency in the radians per second, divided by our normalization coefficient, Cp. So we do 2 pi times 1 mega over the 0.59810 from step 1, and that is 10.51 mega radians per second. So 10.51 times 10 to the power 6 radians per second. Now, if you convert this to hertz, that is 1.672 megahertz. And this value is our cutoff frequency actually for this filter. All right. So what is then the circuit realization? Now you can do it in many different ways for the LC ladder filter. You can do it by what we call the T network. So this is actually here the inductor, the capacitor, and the inductor again. But you can also go for the capacitor, inductor series, and again a capacitor. That's actually the pi network. I go for the T network in this case, and you see here the resistor RS, source resistor, and the load resistor, and these 3 reactive components. Of course, we need to go to the scaled values. That means we need to go from the normalized to denormalized values. And those are given using primes. So we need to use the table shortly in order to go from this value to the actual value we need to use for our final design. Okay, let's bring it up and discuss that in more detail. So we need to go for the scaled component values, and for that we will bring up this table where you see the Bessel response specific for third order, because that's what we needed. Because you also have it for fourth order and fifth order, for example, different values. It is still LC ladder low pass filter, normalized values, and it says still double terminated. Of course, we will go for singly terminated, but you can also use it for double terminated here for specific ratio of your load and the source resistor. And it is also designed for half power frequency of 1 radians per second. Okay, what do we read here? Now you see here the ratio of the load resistor and the source resistor. That can be 1, 10 over 9 I mean, and 1.25. So it goes actually in this case up to infinite. Well, in this case we actually need this infinite. Why? Because our load is some value finite and RS is 0. That means we have here infinite actually. So we need to this last row, and there you see the normalized values for the L1 in our configuration of T network, C2 and L3. So those 3 values are normalized values we need to use to go to the prime values, which are the denormalized values. And we need to use this frequency scaling factor we have found in step 5, and we know that is what the normalization always does. We start from the 1 ohm here. That is always what that's done. And we need to go to the 50. That means we need to upscale this in the magnitude by 50. That's why you see here the km of 50 ohm. 50. Okay, we need to use these 2 parameters to go to the primes here. So what do we do now for the inductor? We need to upscale this using this formula where you see the L1 prime is equal to km, the magnitude scaling factor, divided by the frequency scaling factor times this L1 from the table here, 4631. That is then here 6.964 microhenries. That's the actual value we need to use in our filter here. C2 is done by take C2 prime is then taken as the C2 from here, so 0.8427 divided by the product of this magnitude and the frequency scaling factor, that's then 1.604 nanofarads. And L3 prime is really similar to the L1 prime, just this different parameter from the table. That will be then 1.393 microhenries. Well, how about the resistor RS prime and RL prime? Well, the RS prime and RL prime each multiplied by the magnitude scaling factor because they are independent of the frequency. Now, since RS started at 0, that's the initial value, we also make it 0. But the initial value of the RL, which was our normalized value, was 1, so we do 50 times 1, 50 ohms. So this is the final, these are the final results for our circuits. Okay, let's bring here and summarize here the result for L1, C1, L3, RS and RL. Everything, of course, primed, and these are the final values. And this is now the design circuit. Here up, you see the value for the unscaled, so the normalized situation, where you see the RS is 0 and RL 1. And L1, C2, and L3 are actually these values, these three. And this one is the scaled or the denormalized values we actually need in our final design. So this is the circuit we actually need. You see here again the source resistor of 0, which is actually it's just a short for our source resistor. The load is 50 ohm as required. And you see here the values for L1, C2 and L3, which is calculated. Alright, so we will use this circuit and then verify our calculations in the simulation results using Bode plot. So let's bring up, this is the gain plot. You see the gain and the frequency. And this is then the plot we have in the SPI simulations. This is the circuit. You see here again the resistors and the inductor and the capacitor. And this is a third order. We have designed a third order Bessel response low pass filter. You see here the low frequency gain is 0 dB. The gain is minus 1 dB at 1 megahertz, and there is also a gain of minus 20.8 dB approximately at 5 megahertz. So what do we see in more detail? Low frequency gain is 0 dB. Is this correct? Well, if you look at low frequencies, the capacitors are open and the inductors are shorted. And you see here actually the RL divided by the RS plus RL. Since this is a short, you actually get the complete input signal to the output. So the gain is 1, which means 0 dB. So this is indeed correct. The gain is minus 1 dB at 1 megahertz. This is this green label here, which is actually what we want because we want to have a gain reduction of 1 dB at 1 megahertz. That's exactly as we wanted. So actually these two specifications are now met using this label. The other one is we have a gain of minus 20.79 dB at 5 megahertz, but we needed at least 20 dB decrease, so 20 dB attenuation. So that's also fulfilled. So it's also according to the specifications. You see actually that this is very close to the 20 dB. That's also what you saw in the table, or actually the graph, where you see the intersection, which was already close to the third order. So if you want to really have some safety margin, you can go, of course, for the fourth order. That will definitely create, of course, more attenuation. Maybe you get here 30 or maybe 28 dB then more than what you actually have here. So we have actually achieved our goal. And then also addition here, the cutoff frequency is not shown here, but that is in this case 10.51 megaradians per second, which is actually used as frequency scaling factor. Again, that was then here 1.673 megahertz as our cutoff frequency. So everything is checked. So we have designed this according to the specification and verified this in this simulation results. Alright, was our example considering the design of a Bessel response passive LC low pass filter circuit. And we have done this for a specific situation where the source resistor is 0, and we have looked at the specific ratio of the load resistor and the source resistor in the Bessel response table to design this circuit. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.